Hello, I'm Anna Mackay, and this video is on the area between two functions, and it's a trig example, just the one example. So we are asked to find the area of the region between the x-axis and the part of this function that is below the x-axis in this section. So while you could work some of this out algebraically, you wouldn't know how often this cos curve dips below the x-axis. So that's why you need to create a visual, a picture for yourself. So heading off to our graphics calculators, here is one I've prepared earlier. So here's our cos function in our graph. Thinking about our view window, well, we would use a trig view window, but remember our domain was between 0 and 2 pi. So let's put that in, 0 and 2 pi. Let's have a look. Okay, so it's just this section here, and we only want the bit that's below the x-axis. So to work that out, not only will it be a negative area, we need to know these 2 points. So we're going to have to work that out algebraically. However, while we're here, I encourage you to use your technology as often as you can to cross-check yourself. So while you're here, G-solve, find the roots and write them down as decimals. So we have 4.189 it would round to, an arrow across to the next one, 5.236. Write them down, because let's see what the equivalents are using pi. Now the first one was 4.189. I want to show you what I mean by that. Go to your run menu and type in 4 pi on 3. This is going to end up being one of those values. Your calculator may tell you that. Turn it to a decimal, 4.189. So in a minute, when we find those points, those roots in terms of pi, I want you to check them in your graphics calculator here to see what the decimal equivalents are and to see if they match the two numbers that we read off the graph there, the 4.189 and the 5.236, because there's no point going on with the question if you've already got it wrong at that point in time. You might as well go and fix that error up there and then going on, or getting your teacher to have to find your error later on. While we're here, I just want to show you another one, doing an inverse cos function, because I'm going to refer to this in a minute. I've got written here, I want a fraction, negative square root of 3 on 2, close that off. So that gives us 5 pi on 6. So in a minute I'm going to refer back to this. That's one way to solve things, but it doesn't give you the repeating times of when cos is negative 3 on root 2. So just remember how to do this. Back to our other screen and ready to write. Okay, so we need to find the area here. And first of all, of where it intersects the x-axis. So we need to be putting that equal to 0 and solving. So that's what we're going to start writing. This is a big, complicated function. Most of them won't be this complex, but I thought I might as well do the hardest one I can come up with. Well, it's not the hardest one, but it's got some complexity to it. So we need to solve for x here. So rearrange that root 3 and the 2. So we are solving for this now. So we want to take the inverse of cos. So that's what I was referring to a moment ago. Essentially, it depends on how good you are with the unit circle and knowing these values. I'm going to pitch it to those that, you know, it's not your strong point. You're not doing double maths. So one way to do this is to think of it like you're doing the inverse of cos. And that's what we worked out on our calculator just before. And that told us 4 pi on 3. No, I lied. That told us 5 pi on 6, sorry. Let me explain what that is in our unit circle. So 5 pi on 6 is here, because pi is around at this point, and so we've got 5/6 of that. We're after cos, so that's the x value of what that angle is producing for us, and that's that negative root 3 on 2, and it's a negative because it's in the negative x region. But there's another one in this domain of 0 to 2 pi. There's another time that cos will be negative root 3 on 2, and it's here. And so this first one is 5 pi on 6, which your calculator will tell you, but then you need to be able to work out what the other one is in the domain. So this is 7 pi on 6 there. So these are going to be our two values. Going back over here now, we have 5 pi on 6, comma 7 pi on 6. But we need to keep solving for x, so we need to rearrange and we need to add 2 pi onto each of those, and that will give us 4 pi on 3 and 5 pi on 3. Now, as I was saying before, at this point you've got your two values, which will be your upper and lower bounds. That's where you need to check it with your graphics calculator, because if these are wrong, you might as well sort it out now. So finding out what the decimal equivalents are of these, and 4 pi on 3 we worked out was 4.189, and the decimal equivalent of 5 pi on 3 is about 5.236. And they were the two that we wanted with that cos graph, where we just had that little bit dipping below. The 4.189 was there, and the 5.236 was there. So we're good to go. They're the correct bounds that we need, but instead of decimals, we've got them in terms of pi. Excellent. So 4 pi on 3, 5 pi on 3, here we are. I've written them out already. So now we need to integrate that function between that upper and lower bound, but remember, from that graph, it was below the x-axis, just that little bit there, which means it's going to give us a negative value for our integral, but area can't be negative, so we must take the modulus of this integral. So now let's integrate that using all our skills. So equals, I'm going to put the modulus in last because I like to know how big it ends up being. So integrating a cos function is a sine function, and we need to take into account 1 on a, which is the coefficient of x, but the coefficient of x is 1 there, and we don't need to worry about that. So we actually can just write 2 sine of that bracket there. And plus root 3 is a constant, so we're just going to put x on the end with that one. Put in our bounds, 5 pi on 3 and 4 pi on 3, and then don't forget your modulus. Or if you like to use the negative, put a negative out the front there. Now subbing in our values here. So round brackets, I'll start the modulus and I'll finish it off later. So we have 2 sine, where you see an x, you're putting 5 pi on 3, take away pi on 2, plus root 3 times by 5 pi on 3. Another bracket, subtract off, where we sub in 4 pi on 3 this time. So 2 sine of 4 pi on 3, take away pi on 2, add on root 3 multiplied by 4 pi on 3. Close bracket twice and add in our modulus. Sorting this out a little bit, tidying it up. This part here, feel free to just pop into your calculator. Unless you feel the urge to work it out by yourself. And I can tell you that's -1 there. This tidies up to be not much better. 5 root 3 on 3, not better at all actually. And take away, again this, pop it in your calculator. Oops, it didn't really want red there. That becomes 1. We have plus 4 root 3 on 3 pi. Finish off our modulus. I suppose that's the reason with modulus. You might forget to put the end on, and so it might be better to be using the negative out the front all the time. Up to you. Equal to, we have the -1 here, take 1, that'll give us -2, plus we have root 3 on 3 pi, and our decimal equivalent to that, now feel free to leave it like that, but you need to make sure that's a positive, will be 0.186. If we're to go and check into our graphics calculator using a lower and upper bound of 4 pi on 3 and 5 pi on 3, you would get there, you'd get -0.186. And obviously we want the positive version of that. Units squared is our answer. Great. So that's the end of this video. The next one in the series starts applying things a bit more, and kinetics or motion for integration. Thank you.